Hello everyone. Welcome to the next session on algorithmic problem solving. In this session, we will consider the maximum sum contiguous subarray problem. The input to this problem is an array of integers. The goal is to find a contiguous subarray whose sum is maximum. Now let's take a look at the lesson. The problem and the algorithms are adapted from the classical book Programming Pearls by John Bentley. The maximum contiguous subarray problem was originally studied to get insight into a two-dimensional variant of the problem. The problem and its generalizations have applications in genomic sequence analysis, computer vision, and time series analysis. Let us consider an application. Suppose we have time series data on the daily increase or decrease of the price of an item over a period of time. We would like to know the maximum increase between 2 days. In the example shown, there is a decrease of 6 units on day 1 followed by another decrease of 22 on day 2. This is followed by an increase of 1, an increase of 6, and then a decrease of 5. Finally, there is an increase of 3 on day 6, ending with an increase of 4 on day 7. The maximum increase happens between day 3 and day 7. This works out to 1 plus 6 minus 5 plus 3 plus 4, which is equal to 9. Consider a simple algorithm and a Python code snippet implementing it. For each index position I, iterate through the array incrementing I. For each such I, iterate through index positions j from j equals I to j equals n minus 1. For each such I, j, pair, compute the sum of all the values from a, I, through a, j. We need to track and report the maximum such sum computed. Now, let us analyze the algorithm. There are 3 nested loops. This leads to an order n-cubed complexity. Now let us look at an improved algorithm that uses dynamic programming. For I less than j, let sum 2j denote the sum of the subsequence from I through j. The sum is equal to sum I, j minus 1, the sum of the subsequence from I to j minus 1 plus the value a, j. If I equals j, sum I, j is simply a, I. Here is the pseudocode in Python code snippet for the dynamic programming algorithm. We initialize the maximum sum ms to 0. Then we loop for I varying from 0 through n minus 1. Within the outer loop, we run the inner loop from j equals I through n minus 1, computing the partial sums from I through j. We also update the maximum sum each time the subsequent sum is updated. There are 2 nested loops, with the outer one running n times and the inner one running n minus I times. This gives us an order n squared algorithm. Next, we consider a divide and conquer algorithm for the same problem. To start with, we divide the array into 2 parts. Then, we compute the sum of the maximum contiguous subarray that crosses the boundary of the 2 partitions. This is done in 2 parts. First, we compute the maximum subsequence that starts from the boundary of the partitions and extends as far left as possible. In the example shown, this gives us a sum of 1 plus 6, which is equal to 7. Next, we compute the maximum subsequence that starts from the boundary of the partitions and extends as far right as possible. In the example shown, this gives us a sum of minus 5 plus 3 plus 4, which is equal to 2. Thus, the sum of the maximum subsequence that crosses the boundary between the partitions is 7 plus 2 is equal to 9. Then, we compute the sum of the maximum contiguous subarray residing completely in the left partition. In the given example, this gives us a sum of 1 plus 6 is equal to 7. Then, we compute the sum of the maximum contiguous subarray residing completely in the right partition. In the given example, this gives us a sum of 3 plus 4 is equal to 7. Thus, the maximum sum of a contiguous sequence is 9. Now consider the Python implementation of the divide and conquer algorithm. Consider the array between locations low and high. Let mid be low plus high by 2. Firstly, we compute the maximum subsequence sum MLS starting from location mid to low. Next, we compute the maximum subsequence sum MRS starting from location mid plus 1 to high. The sum MCS of the maximum sequence that crosses the boundary of the two partitions is MLS plus MRS. Then we recursively compute left sum, which is the maximum sum of a contiguous sequence lying completely in the left partition. Then we recursively compute right sum, which is the maximum sum of a contiguous sequence lying completely in the right partition. Finally, we return the maximum of MCS, left sum and right sum. To analyze the divide and conquer algorithm, note that we divide the array of size n into two partitions of size n by 2 each. We can find the maximum sum subsequence that crosses the boundary of the two partitions in order n time. Then we recursively solve two instances of the original problem in the left and right partition respectively. This gives us a recurrence t, n, equals 2 times t of n by 2 plus order n. This recurrence solves to t of n equals order n log n. The fourth algorithm that we consider is a greedy algorithm due to Joseph Cadon. If the value I when added to the subsequence sum is negative, it means I cannot be appended to any existing subsequence to create a maximum subsequence. This also means that no maximum subsequence ends at position I. In this case, we start a new subsequence at position I. Otherwise, we extend the subsequence under construction to position I. This loops through the entire array only once. Hence, we get an optimal order n algorithm. We considered 4 different algorithms for the maximum sum contiguous subarray problem. The results are summarized in the table shown. The brute force algorithm runs in order n cubed time. Dynamic programming helps us in improving this to order n squared time. We can improve this to order n log n with a divide and conquer approach. Finally, Cadon's greedy algorithm runs in order n time and is optimal. Thank you. This course is brought to you by Elahay Technologies.